So a couple precursors. First of all, I'd like to thank Jason and Sebastian for putting together a very interesting workshop. I've had a lot of fun listening to the talks. And like Tero Heikkila, I want to encourage you to interrupt me and ask questions. This is supposed to be a tutorial talk. It's one of the longer talks, so feel free to interrupt. This is the time of afternoon where I sort of like to take a snooze, but I'll try to talk loud enough to keep myself awake and maybe keep some of you awake too. And then last but not least, there are a few of you who've heard me talk on this subject a lot. So you can go to sleep until the last part of the talk when I show you the new data. And I guess the only person who's seen the new data is Jan Arts. So Jan, you can actually sleep through the whole thing. You're giving the next talk, though, so I'll wake you up when it's over. So. All right, so this is work. So I will, in the first third or so, I'll be very generous giving credit to all the other people. And then the last 2/3, I'll just talk about my own group. Forget the generosity nonsense. Just tell you what we've been doing. But this, the whole last part of the talk is in collaboration with Northrop Grumman, but most of the beginning is not. So just, this is sort of how my group has evolved over the years. So the two people who actually started this work on Spin-triplet were Trupti Kere and Mazen Kasane, but all these people worked on various aspects too. And then the work at the end, the newer work I'm going to talk about is really Eric Gingrich, Bill Martinez, Joseph Glick, Bethany Nijelski. She just graduated, now works at MIT Lincoln Labs. Bill Pratt has been very important to me for many years. There he is right there. He now lives in Denver, but he still sends me emails, several a week, about physics in general. So, okay, so I will do an introduction. There will be a fair amount of overlap with Yoshi Mueno's talk this morning, because Yoshi also introduced the topic. But I'll go ahead and show you to sort of the introductory stuff. By now, I think everybody knows Sebastian's sort of groundbreaking work in this whole spin-triplet thing, and then we'll talk about experimental verification. Of course, I'll talk mostly about our work, but mention some of the other work also. And then the rest of the talk will be just about my group's work, both amplitude and phase control of the spin-triplet supercurrent, and then this whole idea of what Northrop Grumman is trying to do, working towards a superconducting magnetic memory. All right, so just to remind you, let me just put the whole thing up now. So proximity effect from a superconductor to a normal metal, you can think of taking a Cooper pair out of the superconductor, plunking it down in the normal metal, so you get these two electrons that want to be on opposite sides of the Fermi surface, but they're not necessarily right at the Fermi surface. But they can maintain phase coherence with each other over times that are proportional to 1 over their energy away from the Fermi surface. So after you average over a thermal distribution, convert this to a length scale, you get this famous length scale called the normal metal coherence length. You can read about this in papers from the 1960s by Dejean and other people. And the point is, at low temperature, these can be very long length scales. These can be upwards of 100 nanometers to a micron if you're at, say, dilution fridge temperatures. So you can have proximity effects that go very, very long distances. When you do the same thing in a ferromagnet, remember, this is a conventional superconductor I'm talking about, so spin singlets. So if you put, by the way, this is not a real ferromagnet. This is a Thiris rendition of a ferromagnet where you just have free electrons with spin split bands, but it's good enough for this physics. So you try to put them on opposite sides of the Fermi surface. You can't do it because this one spin up and the other has to be spin down. So you naturally, even if you put these right at the Fermi surface, you're going to get this momentum shift, Q, which is the difference of Kf up and Kf down. And in this parabolic model, you can express that as twice the exchange energy divided by the slope h bar Vf. So rather than talk about a momentum, I'll think of this as a pair correlation function oscillating in space with this Q vector. Of course, in a 1D model, this would oscillate forever until you had dephasing. In 3D, you average over angles. You get an algebraic decay of the oscillations. And when you have diffusion, you get an exponential decay. So in the diffusive limit, this length scale is actually the same length scale both for the decay and for the oscillations. In the ballistic limit, there is no length scale for the decay. This is just the oscillations. OK, so I think you all know this. And this is sort of the artist's picture then. This is not the gap. This is the pair correlation function. Just I wanted to correct something in one of the slides this morning. Somebody referred to this as the gap. But no, if there's no pair potential in the N or the F, the gap is strictly 0. But the pair correlation function has this, extends into the material. So in the normal metal, it extends, again, these long distances. And you have just a straight exponential decay in the diffusive limit. In the ferromagnet, you get this oscillation and decay and very, very short length scale. Because these E exchange for strong ferromagnets are in the order of tenths of an electron volt. So this could even be less than a nanometer. in something like cobalt or iron. So, okay, the question then is, how do you see this? So this is a bit of prehistory that, so by the way, this physics was understood around 1980 by people like Sasha Buzdin and Bulievsky, these famous papers. Sorry, I don't have their names up here. So people in the 90s were already trying to do things like look at TC of bilayers. So this is a rather famous paper by some people at Johns Hopkins, where they were looking at, I believe this is niobium gadolinium, but I don't remember for sure. And you try to see this oscillatory dependence of TC on the thickness of the ferromagnet. These results turned out to be controversial because when you make thin magnetic layers, you can have dead layers at the surface, and it was a little bit ugly. So this didn't really excite the field. I think the first two experiments that excited the field, this is one of them. This is Takis Kanto's thesis work from Marco Aprilli's group. Here they measured the density of states. So you've got SF, you're varying the thickness of the F, and then an insulating barrier, tunnel barrier, and you're tunneling in from the N into the F. And the point is, when the ferromagnet is thin, you get this typical proximity effect density of states. It looks kind of like BCS, only the amplitude is quite small, right? This is 0.99 here, and that's 1.01. So it's a small effect, but it has the usual shape. Then you make the ferromagnet a little bit thicker, and you notice the whole thing inverts. So instead of having a dip in the middle, you have a peak in the middle. And instead of having coherence peaks, you have coherence dips. So that is that oscillating sign change. So this is one of the papers that I think excited everybody. And the other one, of course, was Valery Ryazanov in collaboration with Jan Arts, in fact, where they did Josephson junctions. So here you do SFS, and you vary the thickness of the Josephson junction. And depending on the thickness, you can get either a 0 or a pi state. Actually, in their first paper, they did this, so they used a copper-nickel alloy, which is a weak ferromagnet. They did that on purpose to make this CF a little bit longer, so it would be easier to control. In the first paper, they actually saw the 0 pi transition as a function of temperature. So they picked a sample that had just the right thickness, and then as a function of temperature, it went through the 0 pi. The actual first experiment that showed it as a function of thickness was back in Marco Aprilli's group, Takis Kanto. So here's palladium-nickel, another weak ferromagnet. And you can see this 0 pi transition. Just to point out, these are not phase-sensitive measurements. These are just looking at the amplitude go to 0 and come back up. But later, people did actual phase-sensitive measurements to prove that these are true 0 pi transitions. So there's no question about that. So in the weak ferromagnets, the Ryazanov group then did it again a few years later. And here they did it as a function of thickness. And they really mapped out 2 full 0 pi transitions. Strong ferromagnets, just look at the length scale here. So the half period is roughly 12 nanometers. Strong ferromagnets, it's much more difficult because the length scale is so short. This is work from Jason Robinson's thesis with Mark Lemire. And you see here in cobalt, the half period is basically a nanometer. So it's just very, very short length scale. They use this FIB fabrication method to make these very small junctions. All right, so that's sort of the prehistory. And so what happened in 2001, 2003 is sort of a series of papers by Sebastian and his thesis advisors. A comment that's quite obvious, which is if you have spin-triplet pair correlations, then you're going to have long-range pair correlations, because now you can put the 2 electrons in the same band. So for these 2 electrons, they don't even know they're in a ferromagnet. They could be in a normal metal as far as they're concerned. So you get this triplet length scale that's very long compared to the singlet. But the second part of their paper, the main part, which is not trivial at all, which was truly the revolutionary discovery, was that you can induce this starting with a conventional spin singlet S-wave superconductor. You can generate these pair correlations using some form of non-collinear magnetization. So their first paper, 2001, they had this picture of a ferromagnet with a domain wall near the interface. I don't think this experiment has ever really been done, but it was a nice suggestion, Sebastian. In their 2003 paper, they did this. They had a superconductor sandwich between 2 ferromagnets. My group actually tried doing something sort of like that. That's not so easy either because, well, actually, things like this have been done, but it's a little bit tough because the superconducting thickness has to be just right. If you make it too thin, TC goes to 0, and if you make it too thick, there's no effect. So you have to be in just the right range for that. But what I'll show you later is, actually very soon, is that you can do a slightly different geometry where these effects can be shown. So the prediction is that normally with with superconductor ferro, you have singlet correlations that oscillate and die out very quickly. That's this dashed line. But that if you have these long-range triplet components, either up, up, or down, down, they will have a very long decay. So we got into this business making Josephson junctions. And really, for us, one of the key papers, although we sort of discovered it in hindsight, but that's OK, was by Uze and Bousden, where they suggested this geometry. So now the advantage of this is your superconductors don't have to be thin. Superconductors can be massive, and you just have 3 ferromagnets in the Josephson junction. Of course, you don't really want to put 3 ferromagnetic layers right next to each other like this because they'll tend to exchange couple. So you need to put some spacers in, and that's what we do. So what we're going to try to do is this idea again of making junctions like this. And if you only have singlet, you should see a very steep decay with oscillations that I didn't even draw in this picture. And if you have triplet, you'll get the long decay. So I think I won't take a lot of time to talk about sample fab. I'll just run through it. It's very standard. We're not doing anything, just this big range of sizes here. If you want to go small, you have to use e-beam lithography. If you go big, you can use photolithography. So it's just ion milling and then covering with an insulator, lifting off top lead. It's all very straightforward. And we actually do have TEM pictures now, but unfortunately, I wasn't smart enough to put any in this talk. So if somebody wants to see some afterwards, I can show you. The measurement is looks incredibly crude. It's just this dipstick into a dewar, but this dipstick is very special. This is where Bill Pratt's expertise was crucial for us. There's actually a SQUID down in there, and the SQUID electronics hooks in through an RF connector up here and goes down in there. So this thing is really a sort of a, well, Jan Arts calls it a SQUID picovoltmeter, and I guess that's the right way to look at it. The noise is in the order of a few picovolts per root hertz. So it's a very nice system. So there's a typical IV curve. These are overdamped Josephson junctions. So that's the standard shape you get for overdamped junctions. There's the supercurrent state in the middle. If I can find my pointer, there it is. And then you get voltage after some critical current. And later in the talk, you'll notice that IC plus and IC minus don't have to be the same. They don't have to be equal and opposite. But that's a subtlety we'll get into later. Nobody's interrupted me yet. That's because everything's crystal clear, right? Either that or you're dozing after lunch, but we'll see. OK, so there is a problem when you use, so when we started working in this field, we were using large areas. We hadn't gone to e-beam lithography yet. And we wanted to use strong magnets for reasons that I won't bore you with now. But when you do that, you have multi-domain strong ferromagnets, and you measure a Fraunhofer pattern. Experimentalists like to measure Fraunhofer patterns to sort of a sanity check to make sure everything's working. So you get something like this, and this, you've never seen this in a textbook. It looks pretty awful. By the way, how did Jason Robinson get away without having this problem? The answer is he made very, very small junctions. And so they were probably single domain, and you didn't have this issue. But in these big junctions, this is a problem. So we had to get over this problem because, remember, we wanted to do systematics as a function of ferromagnet thickness. So the trick we use is one that's very well known in the spintronics community. It's to use what's called a synthetic antiferromagnet. So ruthenium is sort of the favorite metal for this. You take ruthenium spacer, and it works well with cobalt. It works well with permalloy. Does not work so well with nickel. And you put the ruthenium at just the right thickness, and these guys will couple antiferromagnetically. So it doesn't matter if they're multi-domain, like I've drawn here, because domain by domain, you get perfect flux cancellation between the top layer and the bottom layer. So you recover a beautiful Fraunhofer pattern. And it's interesting that all the lobes match the theory perfectly, except for right there. Don't know what happened there, but anyway. And you compare that with one without the ruthenium, and you see it's quite a mess. So that was an important trick for us. That allowed us to use strong ferromagnets and get them pretty thick and still have nice Fraunhofer patterns. So for us, how to generate spin-triplet supercurrent. So we have this nice synthetic antiferromagnet in the middle, and then we add these 2 ferromagnets on the outside, like Uze and Bousden told us we should. And then we have all these copper spacers. These inner copper spacers are just to decouple the ferromagnets. And the outer ones are because we learned in a previous experiment that growing cobalt, well, that was with cobalt, but it's probably true with this too. A lot of these FCC or HCP ferromagnets grow better on copper than they do on niobium. And actually, by the way, this cobalt is FCC, not HCP, but that's a subtlety. Anyway, so here you go. If you leave out these outer two ferromagnets, then the critical current just goes down, 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 down. So that's what we'd call the short-range proximity effect. Now, you might ask, why are there no 0 pi oscillations? Well, that's because not only is there flux cancellation, but there's phase cancellation in these with this synthetic antiferromagnet. So you just get this exponential decay. Now you add these two additional ferromagnets, and you get the red data. So this is the signature of the long-range supercurrent. It tells you it's got to be spin-triplet. There's no other way you can get supercurrent like that through cobalt. Just look at the scale here. This is only 20 nanometers of cobalt, and you've got sort of a factor of 100 more critical current when you add the two extra magnets compared to when you don't. Okay? So what you'd like to do is understand the sort of the role of these outer layers. What happens if you vary the thickness of these outer guys? So let's just fix the cobalt thickness there, where there's roughly a factor of 100 difference, and then vary the thickness of the outer layers. And then you can see when they're not there, you get nothing. When you put them in, you get this huge enhancement, and then eventually you get a decay. Well, the decay is not surprising, because if this thing is too thick, then it's just going to, the singlet part is just going to decay before you even convert to triplet. So that makes sense. Okay, so I do want to just discuss the mechanism. So this is Matthias Eschrig's way of looking at it. It's very hand-waving, and I like it very much because I can understand it. This is not a derivation. This does not give you any of the envelope function. This just tells you, when do you generate triplets? How do you generate them? It also gives you the signs, tells you when you have a 0 junction, a pi junction, or a phi junction. So you can do a lot with this notation. So if you start with a superconductor, you're in a spin singlet state. When you add the ferromagnet, remember what we talked about at the beginning, you have this momentum shift, which you can think of as a oscillation with this q vector. So the up-down picks up this phase e to the iqx. X is the center of mass of the two electrons. But you could also reverse these two, put the down spin over here and the up spin over there, then you pick up minus q. So then you just put in Euler's formula, and you notice that you get back the singlet with cosine qx and the m equals 0 triplet with sine qx. So anytime you have a ferromagnet next to a superconductor, you always generate the m equals 0 triplet, but it's still short range. So this has been there, in all experiments, but there's no particular way of seeing it. To generate long-range triplets, you need to somehow you want the 1, 1 and the 1 minus 1. So what you do is you want to rotate basis. So you put another ferromagnet in at some angle, with its magnetization at some angle, and then you just express this term in the rotated basis, and you see you pick up these two terms, which are the long-range terms. So the idea is, well, the singlet's going to eventually die out. If I make F2 thicker and thicker, this term will die out, this 1, 0 term will die out, and I'll just be left with these two terms. Now, if I want to make a Josephson junction, I put niobium at the far end, it's not going to recognize these. Niobium only accepts spin singlet pairs. So I have to convert back again, and that's what the third ferromagnet's doing. So you convert to triplet, the triplet goes through this thick middle ferromagnet, then you convert back to singlet, and you've got your critical current. So with that in mind, you then look at these data again. Sorry, I want to compare the data. So these were our data where we changed the thickness of the outer ferromagnet, and then I'm comparing it with a figure from this Uzay and Bousdin paper. And the point is, you have to be thick enough at the beginning to generate that m equals 0 triplet, but not so thick that that things decay. And you notice also that with nickel, it comes up faster than with palladium nickel. That's because the exchange energy is higher. So the q is bigger. The wave vector is bigger in nickel, so it comes up faster. Palladium nickel comes up less fast. Copper nickel is has a lot of spin disorder, so it doesn't succeed quite as well. So that's qualitatively fits very nicely. Yeah.
What about can you compare the, let's say, the exchange field coming from here?
Yeah. So we haven't done that. Let's see. I'm trying to decide whether that's because we're lazy or because the band structure of ferromagnets is so ugly. It's one of those two reasons. So the answer is no. We have not tried to do a quantitative fit. I mean, the problem is if you look at the band structure of ferromagnets, right? So it's the bands are very, very complicated, and so the actual the wave vector offset depends on what direction you're going in k-space. So you'd really have to do a microscopic derivation.
But let's assume that you always use the same material, but you always get the same age.
Oh, with the same material.
For example, on geometry, you
I see. That's a much simpler question. I don't know if we have quantitatively tested that. Well, let me give you an example of something that I've always wanted to test, but we've always been too busy to try. So let me go back to that Eschrig. So according to this, you want this QX, so you want the thickness of this first ferromagnet to be such that sine QX is maximum. So you want QX to equal pi over 2. And that's also the place where this term goes to 0. So that means if you were doing just a standard pi junction experiment, where you see the 0 pi transition would be where QX is pi over 2. So that you'd get a thickness of the ferromagnet from that. Now you should take your spin-triplet data and say, where do I see the maximum of the spin-triplet, and does that match? Do those two experiments match? And I think the answer is it's close, but we have not actually sit down and tried to systematically do that for a number of different materials. But that would be one test for what you're asking. And of course, Sebastian will tell me whether there's actually extra phase shifts of pi over 4 that make that not work. But I think that's qualitatively the sort of thing one could do. Okay.
But Norman, I don't think you would ever get real quantitative improvement in that way, because there's also a lot of magnetic anisotropy you don't quite know about. I mean, you think that your magnetization is in the plane, but then it will cancel a little bit.
that type of effects indeed will be kind of
Yeah, of course. A time ago we discussed this question whether actually nickel is perpendicular magnetized rather than in plane magnetized.
This nickel I'm pretty sure is in plane, because we've done magnetometry on nickel films of these thicknesses, and it's in plane. Nickel can go out of plane for some thicknesses, but I don't think it's out of plane here.
No, it's the kind of thing which you also have to take into account. So.
Yeah. Okay, that's about as good as I can do, I think. Okay, so where were we? Yeah, so I just want to mention, just for historical interest, there was this very famous work by Klapvik in 2006. I think it's fair to say when this work came out, the theorists were overjoyed and the experimental community was very skeptical. And so what happened then was in 2010, this was reproduced by Jan Art's group. And then I think everybody believed it, and all sorts of things happened in 2010. Our paper came out in 2010. This work by Jason Robinson and Mark Blimmeyer came out in 2010. This other work by Sprungmann with this Heusler alloy came out. This was sort of tantalizing. They had this, what looked like starting to be a long-range effect, and then there was, when they exceeded that thickness, there was some phase transition, and the whole thing died out, but it was still sort of cute. This is the Arts group again. This work by the Penn State group, which I think is still not 100% understood. This is a cobalt nanowire, single crystal cobalt nanowire with these tungsten FIB, not FIB. Sophie, what do you call these again? Yeah, it is FIB, yeah. So they only see this effect with these special tungsten electrodes, which nobody quite understands. But anyway, the point is in 2010, there were at least 4 groups coming out with strong evidence for long-range spin triplets, and I think Toine Klapvik was very happy because it made his 2006 paper. Now everybody actually believed it. Okay, so these samples I've told you about from our group so far were completely uncontrolled. So Uze and Bousden tell you that you want to get these 90-degree rotations, but nothing we've done so far, we weren't controlling any of the magnetization other than the fact that we had a SAF. So in particular, you might say, in fact, this is what Bill Pratt and I told our student Trupti to do. We said, Trupti, you should magnetize your samples because you're on this triplet line here. If you make all these magnetizations parallel, then you're going to drop down to this singlet line, and your supercurrent's going to drop by a factor of 100. So while she was writing her thesis, she did the experiment, and this is what she got. So this is the field she applied. The measurements are done in 0 field, or close to 0 field, to get the Fraunhofer pattern. But this is the field she applied to magnetize the sample. And at first, nothing happened, and then at some point, the signal went up by a factor of 20. That was after we told her it was going to go down by a factor of 100. So, but Bill Pratt was pretty quick. I remember she came to my office, and Bill was there. And I think within about 20 minutes or half an hour, Bill had figured out why. Oops, that's on the next slide, excuse me. So here's how it works. So we've got these nickel layers that are completely random. So this is an artist's rendition of random domains in the nickel layers. The cobalt layers, if you look carefully at these pictures, I don't know if you can see them, These are more or less random domains, except for they're perfectly anti-correlated. So this one goes to the right, that one goes to the left. This one goes down, that one goes up, et cetera. Because remember, they're in a SAF. So now we apply a field. Let's say we apply a field to the right. We magnetize the nickel. The SAF is a little tricky. So let's say this is the domain of the cobalt in the SAF. The external field is trying to get the SAF to go like that, but the SAF is trying to be like this. So it's a fight, and the bigger the field, the more it scissors. Well, it doesn't matter what orientation it started in. By the time you've done this, they're all like that. When you let go, they all come back perpendicular. So it's called a spin flop. And the SAF ends up spin flopped, perpendicular to the nickel. So what you've done is you've optimized the perpendicular magnetization between the nickel and the cobalt. As it turns out, you've done something else too, which has to do with 0 and pi junctions, but let me get to that later in the talk. So the point is we've optimized the angle, and that's why our critical current went up a factor of 20. So that's, I would say that's a poor man's type of control. We want to do much better than that. So before I talk about that, I'm just going to briefly mention there are other ways to look at spin-triplet. There are many groups that have done these TC experiments. Typically in SFF prime, you can put one of the ferromagnets on the other side. You can do FS, F prime. But I think the best results have come in this geometry. And there are at least 5 or 6 groups, including Jason and Mark have done this. But I think the world record now for TC shift is this work by Jan Arts. So here, I'm not going to go through all the pictures. I just want to show you, this is the delta TC as a function of angle, and it's biggest at 90 degrees. And smallest at 0 and 180. That tells you that you have a spin triplet effect. So Jan can tell you more about that if you're interested. OK, so now I want to move to the control part. So from here on, I'm just going to talk about my group's work. So according to the theory for these spin triplet junctions, there's a couple things you can do. So remember, you have to have non-collinearity between any 2 adjacent ferromagnets in this stack. So in particular, let's say I managed to make the middle one perpendicular to the bottom one. So here I've got everything's in plane magnetization, but I somehow get this perpendicular. And we can discuss how in just a minute. And let's say I can rotate the top one by 90 degrees. So here it's parallel to this one. That means you should not generate any triplet. So that's singlet only, so that's what we'll call the off state. And here, they're all perpendicular. This is the on state. So this experiment requires rotating one of the magnetizations by 90 degrees. The experiment only requires 1 junction, which is nice, but 2 external field coils. So we had to wait on this one until we had a cryostat with two field coils. This experiment over here is where you rotate this one 180 degrees, and this actually gives you a 0 or a pi junction. And you can, in fact, see that from that Eschrig argument that I gave you. I didn't go through all the steps, but this says that if you go right out right, you will get a pi junction. If you go left out right, you'll get a 0 junction. So what's nice about this is you rotate by 180 degrees. So you can imagine having an elliptical junction where you use shape anisotropy to stabilize it. You only need 1 external field coil because you're rotating 180 degrees, but you have to measure with a SQUID because you're looking at a phase shift, not an amplitude. So historically, we tried this one first, but we didn't succeed. And we then succeeded with this one, and now recently we've just succeeded with this one. So I'll show you the successes, not the failures. So we want to make single domain magnets, so we'd like to go to small junctions. This is actually a pretty bad picture. It's got that crazy thing there. But anyway, I actually emailed my students yesterday to ask them if they had any better pictures, but they never take pictures at this stage of the fabrication. But anyway, we make these junctions. They're not particularly small. They're typically 1.25 microns long and 0.5 micron wide, something like that. But the point is, they're small enough and that shape anisotropy should help you control the magnetization. So I just want to show you what happens when you make just a straight SFS with one of these. So you get a Fraunhofer pattern that's now shifted because in addition to the external field, you have the internal field from the magnet. So let's say I start here at high field to the right, so positive field. That means the magnetization is pointing to the right. That means the whole Fraunhofer pattern is shifted to the left. So you can see this fit, well, the data and the fit have a peak over here. Now when you apply the field to the left, you switch, so you notice the sudden jump. And now you're on this other curve. You can sort of see the red points hiding back there, sweeping up. And now the blue points sweeping in the other direction. You're on a curve that has its center over here. So just switching the magnetization, you have these two different these two different curves. So that's what happens when you have a very nice single domain. This is probably the nicest Fraunhofer pattern ever to come out of my group. So that's a single domain magnet switching back and forth. This was actually nickel iron moly. And that particular material, we mapped out the 0 pi as a function of thickness. You can see the first sputtering run, we didn't quite get there. Then we did another sputtering run and sort of mapped it out. So you can see the whole thing there. OK, so now we can make small junctions. Let's talk about this experiment first, the on-off experiment. So this one's a little tricky to describe. So my student came up with this cartoon. He's just drawing the magnetic layers. This is Bill Martinez's thesis work. So he's got the nickel on the bottom, the 2 cobalt layers. Remember, this is a cobalt SAF. And he's using this spin flop trick that we talked about. So if he applies a field in the horizontal direction, the nickel is magnetized, the cobalt has spin flopped, and the permalloy is also magnetized in the same direction. So this is what he calls the on state because he's got everything orthogonal. The top and the bottom are orthogonal to the middle. If he now applies a small field, say, into the board or out of the board, he rotates the permalloy. The field is not big enough to affect the cobalt SAF, but he just rotates the permalloy until it's parallel to the cobalt. That should turn the thing off. So that's what he calls the low state. And then he comes back again to the high state. So here's going from high to low. So this is a function of the field applied in the transverse direction. So he starts like this, and you can see almost happens, and then a little more, he gets it down to here. So he gets a contrast. I think his biggest contrast was something like between 10 and 20. He did it with 3 different samples, and they all had slightly different contrast because it's just a question of how well you can line up the permalloy with the cobalt. So you turn it off that way. Now you want to go back and turn it on. So he applies a field now in the parallel direction, and now he rotates the permalloy back, and he turns it back on again. So that's the on-off control. So there's no, you don't need any phase coherence for that. So that was published in 2016. And then he went on and off just to show you can repeat it. And it's kind of interesting. There's this little training that happens here. We don't quite understand that, but it gets once you've trained it, then it just goes, and he can do this many, many times. It just goes back and forth, on, off, on, off. So that's controlling the amplitude just by rotating. So this morning, I guess, when Dirk Mansky was talking and somebody was talking about rotating d vectors and things, and I think Ilya Tokatli said, well, you can rotate d vectors in a 3-magnet system. This is your 3-magnet system. So this is not the same, of course, as using strontium ruthenate. But I guess, Sebastian, is that correct? You can use this whole d-vector language for this stuff. I don't use the d-vector language because I'm not really in that field, but
for the condensate,
it's equivalent. Yeah.
But are they all in plane?
These are all in plane. Yeah, we'll talk about out of plane in just a minute.
Okay, actually, this P1 dot P2.
Yeah, yeah. So yeah, this whole about whether you can get a phi naught junction. Yeah, when they're in plane, you cannot. You have to have them mutually, not coplanar. There has to be which we can talk about later. We don't have data on that yet, but we will. Okay, so now, was there another question? Yeah.
Just to understand that in this scenario, can you use only one cobalt?
Yes. So the reason we're using the 2 is we're using the 2 for 2 reasons. One is, so we wanted the cobalt to be thick enough so that the spin singlet was suppressed, so that we're seeing predominantly spin-triplet supercurrent. So that's number 1. And then we don't want this Fraunhofer pattern to be shifted off too far in any one direction. We want to be able to measure at low field. So with the cobalt SAF, we get flux cancellation in the cobalt layer. So we only have to worry about Fraunhofer pattern shifts due to the permalloy and the nickel, but not the cobalt. The cobalt gives you 0 shift.
Do you suffer also when the cobalt is very magnetized? Why do you suffer these
the shifts? No, we wouldn't get the multi-domain. If it were fully magnetized, we wouldn't have the multi-domain problem. We just have the shift. The Fraunhofer pattern would be shifted. Right? Just make sure that we remember this. You got it. This thing here. Right, this can be shifted, and in 2D it could be shifted off. And I remember when Bill and I were talking about this experiment, we were envisioning having to do this search in the 2-dimensional field space to find the peak of the Fraunhofer pattern. It turned out we didn't have to do that. He was able to do everything at 0 field, which was nice. But that was going to become a real headache. So, yeah, in fact, basically we made the sample small enough so that the Fraunhofer patterns were broad enough that he didn't have to search in field space to find the peak of the Fraunhofer pattern. He could just measure at 0 field and it was good enough. So, okay, so now I'd like to talk about this experiment. So I told people who know me well that they could go to sleep. Now you have to wake up. These are except for Jan, you can still sleep. These are the new data. So this is something, people who've heard me talk before have heard me show, failed data on this experiment. We now actually succeeded, so I'm quite happy with that. So this is Joseph Glick's work. So I just want to point out, so Tero already mentioned the fact that things don't have to be coplanar, although, so this middle one, you could be, in or out of the board. You could also be up or down. We're going to use the up or down, but in this experiment, we're still coplanar because the bottom and the top are only going to be left or right. So we're not going to do the arbitrary angle experiment. That's for the near future. So it's still coplanar. We're still using a SAF, but now it's a SAF on a perpendicular system. So the perpendicular magnet, we're using cobalt-palladium multilayers. Again, this is well known to people in the magnetism community that this gives you perpendicular, and we've got lots of measurements on that. Again, the ruthenium, you have to find the right thickness, but at this thickness, it couples these cobalts anti-parallel. So this whole thing in the middle is a SAF with perpendicular anisotropy. And you might ask, since we have perpendicular, you might ask why we needed to use the SAF, because when it's perpendicular, it doesn't shift the Fraunhofer pattern. And there it's a little more subtle. We believe that one of the reasons our early work failed was because stray fields, typically these perpendicular magnets have up and down domains. And we were concerned that the stray fields from the domain walls were messing up the magnetization of the nickel and the permalloy. So that's why we went to the SAF. I don't know if that's the right explanation, but I do know that this experiment worked, and the previous ones didn't. So for me, that's good enough. So we're using nickel on the top and then permalloy on the bottom. So this is the free layer. It's going to go left or right. This one is going to be magnetized right and just stays there, and this one stays there. This SAF is very stiff, so it doesn't move at all in the fields that we're talking about. So how do you do the measurement? So this, again, is a phase-sensitive measurement, so you have to use a SQUID. So a SQUID means 2 junctions, and experimentalists in the audience know it's much easier to make 2 identical junctions than 2 totally different types of junctions. So both junctions have the same stack, but what we do is we make one of them very oblong. So this has an aspect ratio of 3. It also has this funny diamond shape that a friend of ours told us should make it even stiffer. And then the one that we want to switch has an aspect ratio of 2, and it's elliptical shape. So this is the one that we're going to switch. This one hopefully will not switch, and in fact, we know it switches at quite a bit higher field. So the measurement through the SQUID is straightforward. So the set field is going to be in this vertical direction. This line over here is a flux line. It just produces magnetic field through the loop so that we can measure the SQUID oscillations. So let me just run you through how we do the experiment. So we initialize with a strong negative field. So everybody, both the nickel and the permalloy, everything's pointing down except for the SAF, of course. And then we're going to do all the measurements at 0 field. We're going to then step the set field up bigger and bigger and bigger and see and wait till one of these magnetic state switches. And after each measurement, after each set field, we'll measure the full critical current versus flux. And then, yeah, go ahead. Yes, moving the trap flux is a very sophisticated procedure. We actually lift the dipstick up while measuring the resistance of this niobium flux line. As soon as it goes normal, we disconnect the ohm meter and then push it back down again. It's incredibly sophisticated. It requires only 1 graduate student and an ohm meter. but it is crucial, by the way. If you don't remove the trap flux, your SQUID oscillations look like garbage. Okay, yeah, I said all measurements are performed at h set equals 0. And we're keeping h set small enough so that only the elliptical bit is going to switch.
Sorry, but then you're cool at 0.
Sorry?
Then you have to cool at 0.
Yeah, that's okay. The magnets stay. The magnets stay. Yeah, we only heat up but just a little, but probably between 10 and 20 Kelvin. And these are all strong magnets, so their Curie temperatures are way, way higher than that. But it's an interesting point, Sophie. If you used one of these really weak ferromagnets, you might heat up so much that you actually went normal and then you'd lose your magnetization. But here we're using nickel, permalloy, cobalt. They're all very, very strong. So heating up to, even if we went to 30 or 40 Kelvin, probably wouldn't matter. So, okay, so here's some data. So I want to show you the 3D plot. So he's plotting, this is flux along the horizontal axis. So you can see these nice SQUID oscillations. This is the set field, so he's starting it, and this is the critical current that we're measuring. This is actually the average of the plus and minus, but that's not important. So you see these nice SQUID oscillations. Now he gradually increases the set field. Nothing happens, nothing happens. He's still getting these nice SQUID oscillations. Then at some point between 15 and 20 Ørsted, suddenly the whole thing shifts. And now you see your SQUID oscillations are offset. And here's just 2 slices through there. This is a slice through the 0 set field data in blue and the 25 Ørsted set field in yellow. So you can see very nice pi phase shift between the two. And then he goes back down again, starting at 0. And this time it comes back around minus 10 Ørsted. He switches back to the initial state. So he actually measured 8 samples. And 7 of them were good. The 8th one, I don't remember what happened, but it was a little screwy. But the reproducibility was very high. So 2 chips, 8 samples, 7 of them were good. This is a second one. Oh yeah, I do want to mention one thing. This is actually a question I have for the theorists. So if the permalloy really switches 180 degrees, then the theory as I understand it says that the IC should be the same in the 2 states, the 0 state and the pi state, regardless of even if the nickel is canted or the cobalt is canted, whatever. The 180 degree flip of the permalloy should give you exactly the same critical current. In these first data set, we got exactly the same critical current, and we were ecstatic. In every other run, the critical currents are slightly different. And even this sample, when he redipped it later, they were a little different. So this is actually more typical. Most of the data sets show this, not only the beautiful pi phase shift, but also the change in critical current. The only reason I'm bringing it up is because I showed these data at a conference in Italy, and Bernd Beck from NIST saw those data, and he said, Norman, the 2 critical currents are the same. That's perfect. You've just nailed it. Every referee is going to believe it. And now every other data set, they're not the same. So now I'm thinking, well, I don't want him to referee the paper. So I am curious if anybody can help me explain that, because we have not written this paper yet, but we are starting to write it very soon. Actually, Joseph's already started working on it.
So what happens with the other junction? I mean, you have
the other junction's not switching at all. We're keeping the field low. In this experiment, we purposely did not switch both junctions. We only did a minor loop. Remember, we're working with Northrop Grumman. Northrop Grumman only wants memory. They only want a minor loop. They just want one junction to switch. And in fact, in their memory, they'll only have one junction. I'll show you data later where we actually show you a major loop on a different type of sample. But this one, we intentionally made one of the junctions as screwy shape as possible so that it would not switch. And we didn't even, I think Joseph did take some major loop data, but he was always worried that if he went too high in field, he might start to mess up the cobalt palladium SAF. So he was very conservative.
the question is, did anything happen?
Yeah. You can definitely switch the other junction, but it's quite a bit higher field. And yeah, the question is, will we even publish those data? I don't know. I haven't looked at them carefully. I've looked at all 7 of these carefully. I haven't looked at the one where you could. Yeah, you should see 2 switches. See, what sometimes happens is the second switch is not as clean as the first one because maybe the other junction is multi-domain. Whereas this junction, the switching was really nice and clean. Yeah?
Sure. By switching the permeable 180 degrees, if you just let it evolve in time, does it relax to the first switching?
No. These are absolutely, remember, these are measured at 0 field. These are absolutely stable. Yeah, so these measurements are very slow. I mean, here's the second junction. So here he's plotted both the upsweep and the downsweep on the same plot. So he started at 0. So remember, he measures this SQUID oscillation, and that actually takes a while because each of those dots there is a full IV curve and extracting the critical current from the IV curve. And then he applies the set field of, I don't remember what his step size was here. Let's see if I can guess. 1, 2, 3, 4, 5. Looks to me like his step size was 5 Ørsted. So he goes up to 5 Ørsted with the set field, sets it back to 0, again measures all these IV curves as a function of flux. Then sets it to 10 Ørsted, back to 0, measures this. So this could go on for, these data is probably a couple hours worth of data. Yeah, some of our runs, well, it depends on the step size and everything. Some of the runs we do are actually the full night. In fact, the student times it so that if he leaves the lab at 6, he'll have data in the next morning by 9 a.m. or something. So, and then here he did repeated switching just to show how reproducible it was. And you'll notice the magnetics on this sample are very good, but not perfect. There are a few dots here where the state was not quite exactly the same. I mean, it's very close. It was certainly the full pi switch, but the critical current just shifted a little bit. Nickel is not a great ferromagnetic material in terms of its magnetic behavior, but in terms of supercurrent, it's wonderful. We get more supercurrent through nickel than any other ferromagnet, any other strong ferromagnet that I know of. All right, so I guess I have 5 more minutes, right? This is probably good timing. Okay, so yeah, why is Northrop Grumman interested in this? So everybody knows that your laptop starts to get pretty hot when you leave it on a long time. And if you think not of your laptop, but you think of supercomputers or big data centers, they use a lot of power. So this is performance in flops. So you're talking, let's see, no, tera is 10 to the 12, right? This is, I just forgot what it's called. What's 10 to the 15? Peta, thank you. Yeah, these are petaflops. And these things you're talking, 10 to the 6 watts, 10 to the 7 watts. Pretty soon you're talking nuclear power plant just to run a supercomputing center. It's kind of crazy. So these people wrote a paper where they tried to predict how much power you'd have if you made a superconducting computer. And they got this line here. Now, I wouldn't take that line too seriously until somebody actually makes the computer. But fortunately, Mark Mannheimer is a program director at IARPA. So he started a program at IARPA to try to actually make. This is classical superconducting computing. It's not quantum computing. This is much easier than quantum computing. It's hard, but it's much easier than quantum computing. So a superconducting computer needs memory. And it turns out these people at Northrop Grumman, Anna Herr is the main memory person. They actually, in fact, she heard a talk by Valery Ryazanov back in the early 2000s. And she immediately thought, aha, there's my memory device. So they have a patent. Actually, they have several patents. This is a picture of the circuit in one of the patents. You don't have to pay attention to the details. All you have to notice is that these funny junctions here, at least one of these has to be a controllable junction. And so the trick is to use one of our junctions for that. And it turns out for reasons that maybe I can go into it during the questions, it's advantageous to control phase rather than amplitude, the way the memory works. So let's just recall back to the start of the talk when we talked about when you just have a single ferromagnet, you get these decaying oscillations. Again, these 2 famous data sets. If you make a system with just 2 ferromagnets, so now forget all that beautiful spin-triplet stuff that I'm so excited about. Just go back to the boring spin-singlet. Well, it's not that boring after all. So what you do is think about if these 2 ferromagnets are parallel to each other. It's just like having a thicker ferromagnet. So you just continue to accumulate phase along this curve. If they're anti-parallel to each other, then majority and minority electrons switch places, and you will subtract the phase accumulation. So if you think of having one layer just thick enough to put you at, say, the 0 pi transition, say at that dotted line, then if the second layer is parallel, it's going to push you to the right into the pi state. If it's anti-parallel, it'll push you back to the left into the 0 state. So you can have a 0 or pi controllable junction just with 2 ferromagnets. You don't have to do this whole spin-triplet thing. And so this is a lot easier to make. And then, actually, this is the explanation for, oh no, sorry, I didn't put the explanation up. This just shows you that this idea of controlling phase has actually been in the literature for some time. This is this paper by Feofanov. So here you have a SQUID. You put a passive phase shifter here. Well, actually, I can just explain it. The point is, if you make this a passive phase shifter, then it never switches into the voltage state. So you put 2 SIS junctions. SIS junctions are very fast. They have large ICRN. They switch very quickly. So this passive phase shifter, if it's in the 0 state, then you get maximum critical current through this SQUID. If it's in the pi state, then you basically get the difference of the 2 critical currents. So, but you use a measurement current then that's in between, well, that's less than the maximum, and then you'll switch only if this is in the pi state, but not if it's in the 0 state. But the point is this junction never switches. So this junction can be slow, but it's just a passive phase shifter. So that's the explanation. So that's what we're going to do. So this you've already now seen. It's the same idea. This was actually an older SQUID design. It's an asymmetric SQUID, not so important. I'm just showing you, again, we've got this flux line here. We've got the in-plane field, and we've got the 2 junctions. This is actually a very old sample where these junctions are humongous. Now they're quite a bit smaller than that. This is sort of 10 microns across, so that junction is probably, I'm not sure how big it is, but it's the fact that you can see it in the optical microscope means it's too big. We make them smaller now. So in this experiment, we actually did the major loop. So I will show you the major loop. And why did the pictures all of a sudden become so fancy? It's because it was published in Nature Physics. We had to do that. So this is, again, the same 3D plot, but now we're going through the full major loop. So let's just look at the cartoons up here. So these are the two junctions. We've got nickel on the bottom, sorry, which one's which? Nickel's on the top, excuse me, permalloy's on the bottom. So we initialize with a big field to the left, all the magnets are to the left, everybody's a pi junction, so it's pi pi. And that's this state down here, this blue state. Now we apply a small field to the right, we switch one junction, switch the permalloy layer. This guy now is in the 0 state, so we're 0 pi, and we get this phase shift. There's also a critical current change, the amplitude change. That's just happens to be the case that for these junctions, the amplitude was bigger at the 0 state than the pi state, but that's not what we were doing it for. And then a higher field, we switch the other junction, so now we're in the 0, 0 state. Then we switch back pi 0, and then finally back to the beginning. So this has now been published for over a year. These are just cuts through the different states, IC plus and IC minus. And this is the average IC so that you can see the pi phase shifts easily. Now you'll notice all these weird shapes and the fact that these are sort of funny tilted sort of ratchet-shaped curves. That has to do with the fact that there's this big asymmetry in the design. So really, only the SQUID experts in the audience need to pay attention to this slide. When you have an asymmetric SQUID like this, you get these funny ratchet shapes. Fortunately, this is all understood. There's this wonderful book edited by John Clark, and chapter 2 is written by Coel and Kleiner and maybe a third person, and they explain all this stuff, and all the equations are there. So you just put it on Mathematica, and you can fit all the data. So in fact, these lines here are actually fits to the SQUID theory. So it works very well, and in fact, you can even look at the parameters. So these are the 4 magnetic states. These are the fit parameters. You see the inductances are rock solid. And the critical currents, each time there's a switch, one junction switches and the other junction stays the same. Except for here. This was supposed to be a switch of junction 1, and junction 2 actually switched bigger than our error. And that's just because nickel is a weird magnet. But otherwise, it's incredibly good. You see at each switch, one of the junctions stays the same and the other junction switches. So that is pretty much it, and I'm running out of time. So let me just say, what needs to be done? Well, for the memory, we're just one piece. We like to think of ourselves as the memory guys, but right, we're just one piece of the memory. You've got to build all the drivers around it, right? You've got to supply all the currents to measure the SQUID. You've got to supply the currents to switch the magnets. That's what those engineer guys do, right? So Northrop Grumman has a huge team of people who are working on all the rest of the memory. And of course, we have to optimize the performance. Nickel has treated us very well, but we really don't like it because it's not very reproducible. So there's a lot of material science that has to be done, develop the read-write electronics. Oh yeah, and then somebody has to actually make the rest of the computer. Oops. So IARPA actually has the C3 program. It stands for Cryogenic Computing Complexity. Actually has 2 parts, the logic part and the memory part. We just work on the memory part, but Northrop Grumman works on both. IBM works on the logic. BBN Raytheon also works on memory. So I think that's it, and that's the summary. That's everything I told you. Thanks a lot for your attention.